going to look at Pascal's Triangle, and the triangle is named after Blaise Pascal, who was one of the fathers of probability. And he's known for a lot of things in mathematics, but what we're going to look at is something called Pascal's Triangle, that you see the first few rows of here. Now, Pascal did not invent this triangle, but he definitely perfected it as a tool in counting and probability. Okay, so how does one construct a Pascal's triangle? Well, if you can see the first few rows listed here, every row starts and ends with a 1. And that's one part of the pattern, and the main part of the pattern is this. That to get that 2, it's the sum of the numbers above 2. So 1 plus 1 is 2. And that brings us to the next row. Those 3's come from the sum of the 1 and the 2 above them, etc., etc., etc. Okay, in order to understand Pascal's triangle, we're going to see how the pattern inherent to Pascal's triangle can help us count an actual counting problem. And this is a well-known counting problem, and it's counting the number of ways we can get from point A to point B following grid lines in some kind of a network or circuit here. So how many ways are there to get from A to B? And before we tackle that one, we're going to do a much simpler counting problem. We're going to just see if we can keep track of the number of ways to getting from A to that yellow dot. Now we're going to make an assumption here so we avoid scenic routes and endless loops. We're only going to go up, or we're going to go to the right, because that would be a reasonable way of trying to get from A to B, since B is located up and to the right of A. So if we start at A, how can I get to my yellow dot? Well, I could go up 2 steps, and then I could go to the right 1 step, and we got to our yellow dot. And I'll swap colors. Another way, we could go right 1 step, and then we can go up 2 steps. And you can probably see one more remaining road if we do a zigzag. If we go up, and then we go right, and then we go up. Looks like there will be 3 possible paths, starting at A and getting to that yellow dot. And again, of course, that's only going up or to the right, are the only motions that we can take. Okay, so how can Pascal's triangle help us count the number of paths from A to this yellow dot? We know that there should be 3 paths. Well, let's see how we can get the numbers from Pascal's triangle to give us the same answer. Well, if we start at A, the only way we can get to those 2 white dots is a single path, since we're only allowed to go up or to the right. And similarly, this white dot up here, there's only one way we can get to that dot. Now it's a 2 steps, but it's still only 1 path. We can only go straight up 2 steps to get to that last white dot I put on the grid there. And we're starting to see some 1s materialize in front of us. So if there's one way to get to this white dot and one way to get to that white dot, how many ways would there be to get to this pink dot? Well, all paths can flow right or up, so we can start to see that. If there's one way to get to this dot, one way to get to this dot, there should be 1 plus 1 ways of getting to that pink dot. And those 2 paths from those pink to that pink dot can both flow up, since we're allowed to go up. And then over here at that top white dot, that can flow to the right as well. And we can see that if we add those numbers, paths together, 2 plus 1 gives us 3. So lo and behold, we can start to see Pascal's numbers appearing on our grid, and it's a lot easier to keep track of those numbers than it is tracing paths with your pen or pencil. Okay, so let's now see if we can piece together Pascal's triangle in this entire grid, and we're going to start to count the number of paths to get from A all the way to B. So since we can only go up or to the right, there's only one way we can get to any one of those vertices or corners on our grid lines there. There's only one way to get up to the absolute top, and there's only one way to get to any of those leftmost points. And similarly, there's only one way to get to any of these points on our grid, because if we're only allowed to go right, it's the only way we can get to any of those lattice points or corners. And that part of our grid as well. And of course, we can see those are all the leading ones and I guess ending ones in our Pascal's triangle rows. And if we allow those paths to flow up or to the right, we can start to see our 1 + 1 = 2 Pascal number. And if you look diagonal, you'll see the 1, 2, 1 row from Pascal's triangle. And if we continue to flow up or to the right, we can start to see Pascal's triangle materialize before our eyes. Now at this point, we're not going to have leading ones anymore, but if you keep following the rules that to any point on our grid, if you're allowed to keep moving from there and go up or to the right, you can start to keep, I guess, or continue to add a pair of numbers together to get now 15, 20, and 15. And if we finish off, we'll get a pair of 35s, and so our answer must be 35 plus 35. There's got to be 70 paths to get from A to B following the guideline or the rule that we can only go up or to the right. Okay, I'm going to attempt to make one more connection here in our intro to Pascal's triangle. Instead of relying on the numbers from Pascal's triangle and superimposing them on our grid to count paths, we can also count this a different way. And let's just take one hypothetical here. Of course, now we're going to still go from A all the way to B. So one way to get from A to B, we know there's 70 ways, but one of those ways would involve something like this. If I can get this to draw straight lines, there we go. And I'll just keep zigzagging here, and I'm kind of taking a random path, but I'm still, of course, trying to get from A to B. So there's one such path, and I ask myself, how many upwards or north motions did I take? And it looks like I took 4, which makes a lot of sense since this is a 4x4 grid. And how many rightward or eastern steps have we taken? Of course, also 4. So this one path here that I drew on the grid is actually in this exact order: a north motion, followed by 2 east or right-hand steps, followed by 2 more norths, followed by an east, and then I gotta go north one last time, and then one more step right or to the east. So north, 2 easts, 2 norths, 1 east, 1 north, 1 east gets us from A to B. And we can start to see this as actually just a series of letters, and 4 of those letters have to be N's and 4 of those letters have to be E's. Let's look for another path. Maybe even a simpler path would be to start from A and go all the way over to the right first, and then go all the way up last. And then you can see how many steps we took here. Of course, I took 1, 2, 3, 4 eastern steps in a row to go all the way to the right. And then, I guess in a different color, we'll go to follow our grid to get from A to B. We finish off with 4 norths. We can see that that is simply another successful way of getting from A to B, and it looks like it's simply an arrangement of the letters, 4 E's and 4 N's. So we can start to think of this as an old counting problem. And I think I'll just say N, 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 and E, 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 E. It's a messed up word, but you can think of this as a word. And how many ways, unique ways, can we arrange those 8 letters in that word? And of course, to count this, it starts off as 8 factorial until you realize you don't have distinct letters. The letters aren't all different. 4 of them are the same. That'll be the 4 N's. And since they're equal, I guess it doesn't matter. And then 4 more of those letters are the same, the 4 E's. And this is a way of counting our 70 paths that we got previously. Now, hopefully you recognize, and this is the connection I want to make, since those 2 numbers on the bottom, ignoring the factorial, adds to the top number, 8, this is actually a combination. This is 8, choose 4, or what's also commonly written as 8, choose 4 in the kind of fancier mathematical notation here. And if you type that into your calculator, you're going to figure out that 8 choose 4 is 70, which means there's 70 paths to get from A to B. And that's relying on our counting chops and combinations instead of using Pascal's method. But that would mean there has to be a connection between Pascal's triangle and combinations. Okay, and to make that last connection hopefully clear, we're going to start to get used to counting Pascal's triangle rows, kind of, I guess, unusually. We have to start on 0. So that second row from the top is actually the first row. So if you start counting on 0, 0 and 1, then yeah, the second row is actually the first row. And that's a bit confusing. So if you can see that red rectangle that I've highlighted, you can see the natural numbers there, 1, 2, 3, 4, 5, 6. That's actually a way to identify what row that you're working with Pascal's triangle. Now, what's the connection with combinations in Pascal's triangle? If you keep your calculator handy or punch in each of these combinations, you can see that that's row 0. And that's not terribly useful, but 0 choose 0 is actually 1 from Pascal's triangle. 1 choose 0, 1 choose 1 are both the number 1. And here for the first time we might have some practical purpose of considering combinations instead of the numbers in Pascal's triangle. So if you're interested in any combination, starting with 2, there's going to be 3 possible combinations that you can do, and it's 2 choose 0, 2 choose 1, or 2 choose 2, and of course that gives you 1, 2, 1, the third physical row in Pascal's triangle, but what we should start to call the second row of Pascal's triangle. And we can fill in at least the first few rows here. Now there's 1, 2, 3, 4, 5, 6, 7 physical rows, but remember, if we follow that diagonal, that'll let us know what combinations that we're dealing with, and that's actually row 1, 2, 3, 4, 5, and 6 highlighted there. Okay, so we'll explore this in a lot more depth and detail in subsequent videos, but for now, at least we hopefully you know what Pascal's triangle is, how to form the first 7 physical rows of Pascal's triangle, and we saw how it can be used to count paths. And it also, we're seeing that there's a strong connection between Pascal's triangle and combinations.